Chapter 5, Torsion, Part A, Example 3, Shear Stress Distribution. In this example, we have a shaft consists of two material, a steel tube, which is bounded with a brass core. This is the outer aluminum steel part, and this is the brass core. A torsional torque applied at the free end of 250 pound-feet, and we do know the rigidity modulus of a steel in British unit is 11.4 times 10 to 6 psi, and likewise rigidity modulus for brass is 5.2 10 to 6 psi or 10 to 3 ksi. Uh, we want to know, we want to plot the shear stress distribution on the cross sections. Let's approach the problem. So for solving this problem, first of all, a solution goes by a equilibrium equation. So the external moment of 200 torsion of 250 pound-feet should cancel out by the two moment, which is one for brass core and the other for outer cylinder of steel. So if we consider the 250 or counterclockwise, a positive direction, counterclockwise goes by a negative. So that's a negative torsion of steel minus torsion of brass, positive counterclockwise 250, convert all that to pound in inch, should go 0. Mhm. And if we call that equation 1. From compatibility, we do know because they are bounded with each other, phi steel is equal to phi brass, and let's call that both phi. And if we go by load displacement equation, it just gives us phi is equal to torsional torque times length of the shaft over rigidity modulus times polar moment of inertia. So if we replace the numeric value for phi for both materials, so torsion of steel times length of the shaft over a polar moment of inertia for steel, which include the outer diameter to the power of 4 minus the inner diameter to the power of 4 times rigidity modulus for steel should goes equal to the same term for second material, which is the brass core. Again, because they are bounded with each other. So in that case, uh, torsional torque of brass times length over polar moment of inertia mm, over times the rig rigidity modulus for brass. 1 and 2, if we solve, and if we call this equation 2, if we solve 1 and 2 at the same time, it gives us a torsion of steel is almost 3,000 pound inch, and if you divide it by 12, it gives you 242.6 pound feet. And likewise, torsion of brass is this much in pound inch, and if you divide that value by 12, which is conversion of inch to feet, gives you 7.38 pound feet. Now let's plot the uh, shear stress distribution, which problems is asking us for that. So for doing that, we know tau is Tc over J. torsion times radius over J. And if we goes that for if we apply that for brass core, that's the torsion of brass times the radius of brass, which is the center material, which is goes by zero point 0.5 inches over polar moment of inertia for brass. And if you do that, it gives you 451 psi. Likewise, for a steel, we need to go by two uh, shear stress. One is minimum, goes by the inner radius of a steel, and one maximum goes by higher outer radius. So inner one for a steel is zero point 0.5 and outer is going by 1 inches. So the minimum tau is 989 psi and maximum tau is just goes for the same torsion but outer diameter and gives you 977. Mhm. The reason of a discontinuity, and you can see here there is a at the interface there is a you get two number, one 451 for brass at the interface and 1989 psi for a tau steel minimum. There is a discontinuity of shear stress at the interface of a steel and brass. Again, as you can see here at the interface, brass goes by a torsion, a shearing stress of 451 psi, but at the same uh, location, just different materials goes by 989 psi. And the reason for that is due to interesting fact that steel is stiffer than brass due to difference in rigidity of modulus. Mhm. If you remember, that's why steel carries more shear at the interface. Mhm. That's the shear distribution, and then from the inner interface from 989 goes all the way to 1977 psi, which is the outer diameter, outer radius. That's the shear stress distribution, while shear strain distribution remains the same, continuous for the entire cross section. And the reason for that is although the shear stress is discontinuous, shear strain remains the same at the interface. And the reason for that is for continuity in shear strain, we know gamma is G of a tau over G. At the interface, we need to go, this is the, let's call that interface, interface of two materials. Uh, Gamma brass goes by uh, shear of brass over rigidity modulus of brass for steel the same. And if you replace the numeric value, it just gives you tau brass is 451 from previous calculation, G brass from problem statement 5.2, 10 to 6 psi, and gamma steel at the interface goes by minimum, smaller radius, tau steel minimum over G steel goes by 989, and both of these over G of steel, which is now 11.4. Both of these calculation gives you a numeric value of 0.08, uh, almost 10 to negative 3 radian. And again, although the shear stress is discontinuous at the interface, like what we saw observed in the previous slide, shear strain remains the same due to the same logic we talk about that. Thank you.